JupyterLab notebook for predictive modeling, which will be the week 4. So what we want to do is understand supervised learning and the concept of regression, which we've talked about previously, implement simple or multilinear regression using Python, particularly using the Scikit-learn package, and then interpret regression coefficients and outputs, and then evaluate regression models using some of these error matrices, MSE, RMSE, MAE, and R squared, and then recognize the assumptions of linear regression and diagnose model performance. So one, introduction to predictive modeling, which is the whole subject of today's learning. Predictive modeling is the process of using data and statistics stroke machine learning. Sometimes we use statistics, and more recently machine learning, but I mean statistics is embedded in machine learning techniques to forecast or estimate future outcomes based on historical or current data. At its core, right, it answers the question, given what we know now, what is likely to happen in the future? That's what predictive modeling is actually all about. So why predictive modeling matters? Predictive modeling turns data into actionable foresight. In other words, we pick up data and then we can essentially predict the future. It helps organizations anticipate trends, optimize operations, personalize user experiences, reduce risk. There are all kinds of things, right? Because if you have enough data, then you can do all kinds of things, predict what can happen. You can literally tell what the future can be, though albeit in a very limited manner. So examples, for example, Amazon recommends products to you. You're watching a movie on Amazon Prime, all of a sudden you begin to see all these other movies that are similar to what you have watched, because it feels like, oh, this is the kind of movie they're interested in. So it begins to recommend those. And that's all predictive modeling. Banks can detect fraud. They already, over time, they're able to say, hey, fraud is likely going to be committed by a person that has this profile or within this neighborhood and all of that. Usually dependent on data. Hospitals can predict patient readmission, and there are variables that feed into that. That would be an example. And manufacturers predict equipment failure. So sometimes instead of waiting for an equipment to fail based on historical data, they can actually predict that a particular equipment has a likelihood of failing, 85% chance of failing after 6 months. So instead of waiting for the equipment to fail, they essentially change that equipment once it hits a 6 months mark. That way they do not have a downtime in their operations. Now, how predictive modeling actually works. So it typically follows these steps. First of all, you have to define your problem. Very, very important. And that's why even as a data scientist, you have to be working with a subject matter expert. And some of the questions you all need to be figuring out what are you trying to predict. That's at the core of everything. Then number 2, is it a value? Are you trying to get some kind of output, a fixed value, or are you trying to predict a class or category, right? Am I looking for bad or not bad? Or am I looking for just groupings, right? And that will be classification. But if I'm looking for a specific output, right? Like how much is the price of a house, right? That's not a category, it's a continuous output, right? That would be referred to as regression. So the next thing I want to do is I want to collect the data. You need to know what data you're trying to collect. So, and the historical data that you collect should include the features, which is the inputs, right? That can help you get your outcome. Your outcome is usually what you also refer to as the target. Data processing is the next one. Now you pick your data. We've done this in week 1, 2, and 3, particularly week 3. You handle that. If there's missing data, there are different ways to handle missing data. You have outliers, different ways to handle outliers. Refer to week 3 videos. Normalization. Sometimes you have to normalize the data, you know, and then you might have to encode the data. So for example, if something is yes, no, the computer can't ingest yes, no. You can decide, okay, my yes is 1 and my no is 0, and then you feed it into the system so that whenever the computer sees 1, it means that you are saying yes. When it's 0, it means that you're saying 0. Or I'm trying to predict something. There's something called one-hot encoding. I have 5 things to choose from, right? And that's often in the realm of classification. I have 5 things to choose from, but at any one time, only one of them is correct. So in that case, right, and I use 0 and 1, so the 4 things that are not true at that point will be 0, 0, 0, but the one that is correct will be 1. There are ways to code that in your data, but essentially that's where encoding comes in. Feature engineering. Features are essentially the inputs that you need to produce the results. Mentioned that in the past that you want to buy a house, you want to know the price of the house, and because you buy houses all the time, you have approached someone, a data scientist, to build you a data product that can help you. Once you get all the variables about a house, you enter it and it will predict what the fair price is. But all of that information that you give to the data science to build your data product for you, all of those are features. Now, all of those features are not necessarily born equal. For example, the paint of a house, the color of the paint of a house might not be as predictive of the price as the number of rooms in the house or the neighborhood where the house is. So feature engineering is essentially it can help you, select the right input, right, to use for that model, right? So feature engineering is essentially creating, selecting, or transforming variables to improve your prediction. Model selection. Eventually, you're going to have to choose a model and there are literally hundreds, if not thousands, of models that you can choose from. Though some of the most popular ones are like what you have here, linear regression, decision tree, random forest, XGBoost, neural networks, and all of that. So there is a model selection process. And for you to effectively choose the right model, you need to know what those models are, what they do, and all of that. So next, you have to now train the model. And what it essentially means to train the model is to fit the model on a labeled training data. What does that mean? So if I get a data, I need to be able to tell you what the output is, right? If I do that so that eventually when I give it to train it, I already have the actual answers, you know, so that after it trains, I can use my test data to test it, and the test is usually the output that was predicted versus the output that I already have, and that would help give me my error. And if the error is very small or non-existent, then that my model works well. And the way the matrices that we use to measure all of that is what we have here, like RMSE, MAE, accuracy, um, mod accuracy models, precision, and all the other cohorts, F1 score, AUC, ROC, they are used to assess the performance of the data. So eventually you have to deploy, and that's where you have data scientists doing some of that work and sometimes data engineers. And then you have to monitor and update. Sometimes the environmental factors that have on the basis of which the data was collected might begin to change. And when that changes, guess what? Your model might, even though it was highly accurate, high performance, all of a sudden you see it might not be performing well. So it's your job as a data scientist to detect that drift and to retrain using more new data as you go on. So there are different kinds of predictive modeling, like we mentioned. There's the regression, where you're trying to predict a continuous numerical outcome like the price of a house or temperature, or you're trying to do classification. If you put in some values, I want to predict whether this is a boy or a girl. That's categorization. I want to predict the color of the ball based on some values, right? Or I want to predict whether something is a spam or not a spam. That's where classification comes. You predict discrete class labels, right? So like spam detection or disease status, right? Is he sick or is not sick, right? And then there's also time series forecasting. We predict values over intervals, right? Usually a lot of variables are data is generated for a lot of variables over time. So at the end of the day, your dependent and your independent variable will be time and some value. In those cases, right? For example, one of those examples is stock price. You know, if we want to find stock price, right, we are always going to ask on what date, on what day, at what hour. At every single second or every minute, you can predict a stock price. That example will be a time series data, and then we can actually forecast that kind of data. You know, we can forecast demand, we can forecast all kinds of things. And then there is also the survival analysis, which is another type of predictive data. This is helps us predict time until an event occurs, right? For example, customer churn or failure time. That's what a survival analysis is all about. So we are going to go into supervised learning. Very important. Normally we have supervised and unsupervised learning, and here we're going to focus on supervised learning. So it's a type of machine learning where the model is trained on labeled data. In other words, you need to give me all of the answers. Tell me what this means. It's almost like what happens when you're training a child, right? A child comes into the world, does not know what a ball is, or does not know what a plate is, does not know what a table is. So how do you train the child? You show the child a ball and say, ball, ball. You show it all kinds of things. Over time, based on you labeling each of those things, the child is able to know what those things mean. The next time you present a ball to him, the child just says it's a ball because you gave it that information. That's different from supervised learning. In supervised learning, you just give it all of those things and it figures out, it looks at the patterns, looks at all kinds of things and begin to separate things into clusters, right? That's different from supervised learning. Regression, which is a type of supervised learning, which is regression, which is a type of predictive modeling. You use regression algorithms when you want to predict a number. In other words, predict a continuous numeric outcome that can take on infinite possible values within a range. In other words, it could be 1.1, 1.2, 1.3. It could be 100. It could be 1,000. That output is going to be it could be an infinite possible set range of values. Regression is used when the output variable is continuous. This is an example of what a continuous variable is. A variable that can take any value on a number line like 3.4, 15.75, and that's what regression analysis does. Regression in itself is predicting a continuous output, and this is what a continuous output is. So examples of regression use cases, I want to predict a house price. Notice how this is a fixed number, a continuous variable. Price is a continuous number, so it could be anything. Or I'm trying to forecast temperature. The temperature, could be 1,000 degrees Fahrenheit, but temperature varies continuously. I want to estimate fuel efficiency. This is also a continuous variable. And then blood pressure, it's not a discrete, not discrete categories. They are also fairly continuous. So what is not a regression, which would be a classification instead? If the output is a category, e.g., I'm trying to figure out whether the email is a spam or not a spam, that's a category. I want to find out whether it's a cat or a dog, that's a category. So you use classification, not regression, for problems like that. So if I give you different features, right, and these are the regression, and this is what the classification would look like. So for the output type for regression, it will be continuous numbers. For classification, it will be discrete categories. It's either A or B. For the goal, we are trying to predict a number. For classification, we are trying to predict a category. An example of an algorithm that you can use for regression will be something like linear regression, decision tree, and regressor. For classification, we have logistic regression, random forest classifier, and all of those kind of things. Sample output. This is what a typical output for a regression model would look like. Continuous numbers. For here, for classification, it will be approved or denied, cat or dog, boy or girl, rich or poor. So those are classifications. Particular use cases, a particular use case for a regression model will be to predict house prices or fuel cost or income. For classification, what I'm trying to classify is email, spam detection, disease diagnosis, all of those kind of things. So now we are going to look at a particular case of regression, which involves a continuous output. We're trying to create a scatter plot of a house, house size versus the house price. Yeah, if we look at this is, we say this is our house price, right? And we want to create an array for that house price. That's how our house price, house size here. This is the size, maybe square feet, 1,000 square feet, 1,200 square feet, 1,500 square feet, all of that. House price, maybe $150,000, 180,000, blah, blah, blah. So I have my house price and house size, and I have my house price. Now, my coefficients, right? To find my coefficients, I can use my NumPy and use a method called polyfit, in NumPy. Let's do NumPy. See what it does. NumPy polyfit is a NumPy function used to perform a least square polymer fit. In other words, all we're trying to do is to create a fit, right? And this right here is the function for doing it. Coefficient is equals to, yeah, same thing. So you can read things like this. So this is a fit that has been created right here. So that's what this is trying to do. And then we also want to include a regression line, right? It helps to define the polynomial function. The polyfit is relationship between the x and y modeled as an n degree polynomial, right? So next thing we do, and I included some resource here if you want to read up a little more on it. Next thing we do is plot the scatter. This is your scatter, which is the lines in blue. Then we want to now plot. What are we plotting? Look at what we are the house size and the regression line, right? We want to put both of them here, and that's what you have here. Then we have the title, size, blah, blah, blah. So this is what the actual is, and then this is a regression line, house size, and then the regression line. So this essentially tells us that as the house size increases, the price of the house also increases, and it's almost like a perfect match. So, and this is the red is what was predicted, but then when we mapped the data, actual test data that we have, it came close to, you know, what's this. So in other words, our test data actually says, so the red line will be your model, and then the dot 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 will be your test data that was used to check whether the model, you can see a little discrepancy here. It doesn't really fall exactly on the line. So the difference between this point and this point and as this point and this point, and everywhere, you add all of it, and that's how you get to come up with those matrices, right? Like MSE, RMSE, MAE, and all of that. So this visually shows how regression fits a continuous line through the data. Next thing, let's look at an example of categorical output. Categorical output, not complicated, same thing. I'm loading my plotter, Matplotlib, that helps me do plots. I'm loading NumPy that helps me handle numbers. And then I'm creating an array of a certain number of, exam scores. So I use np.array. And the other thing I'm doing is based on this data, I'm trying to tell it what my labels. Remember when we're talking about supervised learning is you have to provide the label, right? So this is how you provide the label. So I have all of these exam scores. Maybe John made 40, Susan made 45 in the exam. This person made 70, blah, blah, blah. But I have to label to tell the model, right, what each of them means, because the computer doesn't know whether it's a pass or a fail. You are the one that will determine that it's a fail. So I'm trying to say 1, 2, 3, 4, 5, which is 1, 2, 3, 4, 5, right? All of these people passed. So how do I represent pass, right? I tell it that 1 means pass, 0 means fail. So for each of them, I map 80 is 1, 75 is 1, blah, blah, blah. 40 is 0. In other words, if you got 40, you failed. 45, you failed. 50, you failed, and all of that. So I've created the label. So now I have these two things to work with. So I want to plot a figure, right? So I said for score, score and label. So I have my score, I have my label, right? For score and label, zip. Zip is a type of function that is used to put together two variables to create a tuple. And a tuple is some kind of way of putting together two or more data, but it's immutable. In other words, it can't change. That's okay. I think it talks about it. The zip function pairs two elements from the two list into a tuple. That's what it does. So I'm now saying if my label, which is this, is equivalent to 0. In other words, if this person failed, then print a scatter of the score label, and the color has to be red. And then the label, you say, hey, they failed. If not, you do this. Else, in other words, if the label is not 0, but the label is 1, then do this. That's what we have. Then the other thing I want to do is I want to introduce my cutoff. In other words, by looking at this, I don't know where the cutoff between pass and fail is, right? But I can establish that using this line of code. In other words, I'm saying that my cutoff is X equals to 60. Anybody that gets lower than 60 failed. Anyone that gets, more than 60 passed, right? So the color is black, and I want to, what I'm and I'm going to create a line, a boundary line. So this is that boundary line that was created. This will give me all of this red, and you can see this is green. This will give me green. Where is my green? Color green, right? So if I run this, that's how you get this. So you can essentially look at this and know the people that passed and those that failed, you know. So R dot is for fail score. Any score less than 60 is fail. Any score that is greater than or equals to 60 is pass. So, and the dashed line at 60 shows the decision boundary. Another way to look at this is to, this is one method, but we can also decide to do what we call logistic regression. If you go back up here, logistic regression is also used for categorical data. Let me see if I can find it. Logistic regression is used for categorical data. Yeah, that's classification, logistic regression, right? Which is different from linear regression. This is logistic regression. So let's go. So for logistic regression, if we decide to, it's almost the same thing that we're doing, but now we are creating a line of fit here, right? That's what we are doing. It's almost like what we did here, but now we are creating a light line of fit to show the curve. So we import all of the information we need. Then the same thing we did before, you know, and then our array, we decide pass, fail, pass, fail. And then instead of using any other model, now we are using a model, the logistic regression model. And then we're trying to fit our X against our Y. That's what we're trying to do. And then we come up with, in this particular case, you can see what we are doing. We are deciding what our test data is, right? And our, oh no, so we are creating smooth score range for plotting the curve. That's what we're doing here. And then this is our probability of passing. And then you plot the actual data. What we're doing is now plotting the actual data when it's a pass or it's a fail and all of that. And then you plot, this is you plotting the data, so the parameters for the plotting, and then this is your decision boundary that we created before. You can see the decision boundary here. This right here is for the curve. And then you run something like this, and that's a case of logistic regression. So we can tell these are fails, so that's logistic regression. And then you can see there are a few things here like reshape, what they all mean. Look at your reshape here. You would have seen where it says something to reshape. It's trying to tell you what all of those things mean. You can read up all of that here. So there are different kinds of regression. There's this simple linear regression. We only have one predictor and one continuous output. We talked about that in the last two lectures that we also did. You have one predictor. In other words, you have one target and you also have one feature. For example, I'm trying to predict the price of a house, you know, but I only have the size of the house, something like that, right? Or I'm trying to predict salary from years of experience. So it's your salary versus your years of experience. But multi-linear regression is when you are trying to predict, say, the price of a house, but you're using multiple variables like the size of the house, the location of the house, how many floors are on the house, all of those things, right? That's multi-linear regression. And then you also have polynomial. This is a case. Polynomials is usually when you now have all these curves. There is a non-linear relationship And that's what your polynomial curve models. You're trying to model learning curves, or there's one called ridge or lasso, which is your regularized regression to prevent overfit. So it's your typical regression, but now you're beginning to build in capabilities to make sure that what am I calling it now, that overfitting does not happen. This is for high dimensional data sets. So tools for regression in Python, these are some of the tools, and we've used some of these already here. You can see linear regression, some of the things you want to do, the steps. That's a typical workflow. You import the libraries. We did that above. You load the data. You split the data into training and test data. You create and train the model. You make predictions. You evaluate the performance and visualize the results. This again is a simple linear regression. I will stop here because we've already gone through this multiple times, even in previous videos. But if you go through, you can actually understand what's going on here. Same thing, load your data. Here in this particular case, load your packages. Here, we did not copy in some data. We just use the randomizer, right, to just generate some data, right, for the X and Y. So it's very random. In other words, each time so look at how we are. If we run it again, it will get, it might keep getting slightly different data because it's random. Yeah. So let me try to make it 1,000 instead of 100 so that it will give us more data points and see what this looks like. Okay, see what we have now. So if I even make it more, let's make it 500. It will generate random data too, less dense than what we have now. And let's run it and see what it will look like. Okay, this is what it looks like. There's an outlier somewhere there. So let's go back to 1. Go back to 1. And then this is what we have. So train or split, notice this is what the function is from Scikit-learn model selection. It randomly splits your data into 2 parts, right? Your training set used to train your model and your test set used to, so that's what train test split. You would have seen it somewhere here where it does that. Should be somewhere here, but up here, just check it. So what else? Next thing, some of those evaluation matrices that we talked about, these are what they are. And then we did talk about this in the slide for exercise 4, linearity, independence, homodystacity, and heterodystacity. We talked about all of that, normality, and you can read up more on this. And then this is a typical example of multilinear regression, right? And look at the sample data we are creating here. Now it's not just one data, we are loading up different variables, in other words, different features, right? But then we are analyzing it against these outputs, right? And then we are using this model, a linear regression model. It's still a linear regression model. The only thing that changes is that your parameters are more in trying to, so it's a multiple linear regression, right? And then what else? This is your how to predict your Y, which is your output. And then we also have your R squared. These are what I was showing us here, the regression evaluation matrices. That's where you load them up in and then you print them out. And after printing them out, this is kind of what you get, right? Which is your predicted exam score versus your actual exam score. And this is what you have. So good prediction right there. So your inputs, 2 features, hours studied, and exam score continuous. The model learns how each input contributes. Yeah. So what else do we have? Let me run this. Oh yeah, this right here is looking at two factors, and that's what it describes here, up here, right? Two features: hours studies and attendance. So the hours that are studied and the attendance. If you use the hours studied versus your attendance, you run that and you get something like this. What else do we have? I think so. The idea is to go through all of this. And sometimes for your model linear regression, you can actually plot a 3D plot of it to see how it's just like when you have your XYZ, it's hard to visualize it as two dimensions. You can now visualize it in another way to see how two or three or more factors, right, are related to each other. And that's what you have going on here. You know, so this is not turning. There are times where you can actually flip it around and turn. I think I have it in as some other slide. Okay, this is the interactive one. Yeah, where you can sleep and look at how all the factors are related. So now I'm looking at three factors, right? How is exam score, hours studies, and attendance rate related? Because that will require XYZ components. So if you turn it around, you can see how that relationship exists. So if I look at it this way, I can see the relationship between exam score, attendance, and the hour study. So, and that's the code to get us there. And I think we are done for this topic. Yeah, if you have any questions, just drop it, send me an email, drop it in the chat, and then we will talk about this some more.